Swayam Prabha. Digital India. Educated India.
Dear all, we are going to continue the next important theorem is called it as Chinese remainder theorem. This is most useful for understanding for simultaneous congruences. We come across only linear equation and then product of two variable is identically equal to 1 under modulo n we come across. Suppose the linear congruence simultaneously comes, how to attack the problem. Now, before going to see the problem, first of all we should know what is the Chinese remainder theorem. Chinese remainder theorem is used to solve set of congruent with one variable but different moduli. So, these are all different moduli, that is M1, M2, M3 and so on Mk, which are relatively prime as shown below. Say you take two numbers M1 and M2 and the GCD of M1, M2 is 1. Similarly, M1, M3, M1, M4 and so on M1, Mk, and parallelly we have to check M2, M3, M2, M4 and so on M2, Mk. So, this is called it as the system of the linear equation simultaneously it will come, then it is said to be a system of what linear equation under modulo. So, this statement is called it as Chinese remainder theorem statement. And the theorem further can say is that the detailed statement of the theorem is M1, M2 and so on Mr are pairwise relatively prime integers. It means M1, M2 check, M2, M3 check and so on, R minus 1 into Mr check it out, and similarly M2, M3, M2, M4 and so on M2, Mr, and all the pairwise numbers you have to check it out. The GCD of the pairwise numbers are equal to 1. Then one it is said to be pairwise relatively prime. Relatively prime means the GCD of two number, the GCD of two number is 1. Okay. So, keep it in mind this is the first assumption you have to do. Next assumption you take A1 to AR be the integers, the system congruences already we come across x is identically equal to ai under modulo mi for 1 less than or equal to I less than or equal to r has a unique solution. Then we can write capital M modulo m is product of these m, m1 into m2 into and so on mr that you call it as capital M, which is given by x identically equal to a1 m1 into 1 I y1 and a2 m2 into y2 and so on ar mr into yr under modulo m, where mi is equal to m divided by mi and yi is identically equal to mi whole inverse under modulo mi for 1 less than or equal to I less than or equal to r. So, this is the statement of Chinese remainder. So, we need every time the inverse of m, and then we come across how to find out the inverse of m under modulo. So, keep it in mind of this previous theorems in the previous module, so that this modulo of the numbers can easily understand. So, the proof is very simple, that we can notice that the GCD of mi comma capital Mi comma small mi is 1, that is relatively prime to one another for 1 less than or equal to I less than or equal to r. Therefore, the yi all exit determined easily from the extended Euclidean algorithm. We done it already, refer it. So, we notice that mi into yi is identically equal to 1 under modulo mi. We have ai into mi into yi is identically equal to ai under modulo mi for 1 less than or equal to I less than or equal to r. So, on the other hand, ai into mi into yi is identically equal to 0 under modulo mj if j not equal to I, since mj divides mi in this case. So, now we see that x is identically equal to ai under modulo mi for 1 less than or equal to I less than or equal to r if x naught and x 1 were solutions, and then we would have what the difference of this x naught minus x 1 identically equal to 0 under modulo mi for all I. So, x naught minus x 1 identically equal to 0 under modulo m. So, they have a same modulo m. So, this way we can understand the proof of the Chinese remainder theorem of simultaneous congruence relations. Now, let us go with one example. Solve the system x is identically equal to 3 under modulo 6 and x is identically equal to 5 under modulo 7, x is identically equal to 2 under modulo 11. Now, the solution is, you see 6, 7, 11 are relatively prime to one another. Compare with 6 and 7, 7 and 11, 6 and 11 and 7 and 11. So, all are the GCD of the pairs is 1. Therefore, they are relatively prime to one another. So, the system is solvable and apply Chinese remainder theorem is applicable. So, let m1 equal to 6, m2 equal to 7, m3 equal to 11, call it as, and capital M is a product of m1 into m2 into m3, which is equal to 462, and yn is defined by m1 capital M by m1 into y1 you have to write. So, that capital M is 462 divided by what m1 is equal to 6. Therefore, divide them 462 by 6. So, the resultant is 77. So, that 77 y1 will come. So, under modulo 6 of 77 is minus 1. So, minus 1 into y1 identically equal to 1. Therefore, y1 equal to identically equal to minus 1 under modulo 6. So, one of the values we got it. Similarly, you go to the next capital M by M2 equal to 66 because 66 into y2, that is here, that is y2. So, capital M equal to 462 by m2 is 7, and simplify we have 66, and then you substitute here. Therefore, 66 into y2 under modulo 7 of 66 is identically equal to 3 under modulo 7. So, that is 3 y2 is identically equal to 1. So, using the inverse technique that 3 is a corresponding inverse under modulo 7 find out. So, that 3 into minus 2 is minus 6 under modulo 7 is 1 will come. Therefore, y2 equal to minus 2 under modulo 7, and finally, we have capital M by m3 into y3 which is equal to capital M is nothing but 462 by m3 is 11, and then the resultant is 42 will come. So, 42 y3 is identically equal to 1. So, 43 is under modulo 7 is minus 2 y3 is identically equal to 1 under modulo 11. So, that y3 is equal to what 5 under modulo 7, because the inverse of minus 2 is 5. So, that we have y3 equal to 5, it follows that the system, the solution of the system. So, it follows that the solution of the system is x is identically equal to capital M by M1 into y1 b1 plus capital M by M2 into y2 b2, capital M by M3 into y3 b3 under modulo M. So, that first case we have a 77 and y1 we got it here, y1 got it, and then the b1. So, the b1 is corresponding to value is minus 1. So, b1 is corresponding to 3, right. So, the corresponding b1 you have to calculate with the modulo, that is you have a question b1 that is x is identically equal to b1 under modulo m1 and x is identically equal to b2 under modulo m2 and x is identically equal to b3 under modulo m, given b1 equal to 3 and b2 equal to 5 and b3 equal to 2. So, refer the given question and substitute in this expression capital M by M1 into y1 b1 plus capital M by M2 into y2 b2, capital M by M3 into y3 b3 under modulo M. So, we have what 77 into minus 1 plus into 3, then 66 into minus 2 into 5 and 42 into 5 into 2 under modulo 46, 462. So, that the resultant of this number is 453 under modulo 463. So, this way we can find the value of x. So, once you can substitute the value of x in the given problem, beautifully it satisfies the solution to the problem. Next we have a example to select a number less than 105 which has the remainder a, b, c when it is divisible by 3, 5, 7 respectively. The solution is the selected number is the remainder of what 70a plus 21b plus 15c with respect to 105. So, this can be proved as under the following the result reduces to the solution. So, this will come based on the question like this. So, let us see this statement, right. Finally, we will see this statement. Now, from given statement x is identically equal to a, we do not know, therefore, a you have to put it under modulo 3 and the given problem can be written like this: x is identically equal to b under modulo 5, x is identically equal to c under modulo 7. So, the problem can be written like this and then the first statement we have to bring it. Now, here the moduli is 3, 5, 7 are relatively prime. First you check it out, they are relatively primes or not. Here relatively prime because the GCD of 3, 5 is 1, 5, 7 is 1 and 3, 7 is 1 and they are relatively prime to one another. By Chinese remainder theorem applies, M1 equal to 3, M2 equal to 5, M3 equal to 7. Therefore, capital M equal to 3 into 5 into 7 which is equal to 105. Now, according to the theorem, Chinese remainder theorem, we have to determine the value of what capital M by M1 into Y1. So, that is given, it is 35. So, it is not given, we have to find out. So, M, what is M? M is equal to 105 and then M1 equal to 3, therefore, 105 by 3 is 35. So, here 105 by 3, right. So, it becomes 35. Then we have what 35 y1 under 35 the modulo 3 this is equal to minus 1 modulo 3. So, this value become minus 1 into y1 which is identically equal to 1 under modulo 3. So, this implies we have y minus y1 identically equal to 1 under modulo 3 is 2. So, y1 is identically equal to 3 under modulo 3. So, similarly we have to go with second part. Similarly capital M by M2 into y2. So, capital M is 105. So, here 105 by M2 is nothing but 5. So, 105 by 5 is 21. So, 21 under modulo 5 you check it out. So, which is identically equal to 1. Therefore, 1 into y2 is identically equal to 1 under modulo 5. So, y2 value we got it. So, y1 value we got it. Now, we go to the third part, capital M by M3 into y3. So, what is capital M? Here 105 by M3 is equal to 7. So, this divide we have what is 15. So, 15 y3 is identically equal to 1 under modulo 7. Therefore, 15 is identically equal to 1 under modulo 7. Therefore, y3 is identically equal to 1 under modulo 7. Thus, the solution of the system is x is identically equal to capital M by M1 into y1 into B1, that is A, and capital M by M2 into M2 into y2 into B we do not know, A we do not know, and then finally end up with this is C. So, 15 into 1 into C. So, 15 comes because of what, capital M by M3 into Y3, and then corresponding the value this is 1, and then we do not know the value of C under modulo 105. Therefore, it becomes 70, it becomes 21, it becomes 15C under modulo 105. So, already we checked the value of this one in the given problem. So, it derived. So, this way we can write x is identically equal to 70A plus 21B plus 15C under modulo 105. So, this way we can find the solution to the problem. Now, which is the result we require? Suppose the person selects the number of tells you that A equal to 2, B equal to 4 and C equal to 3, then simply substitute it on the last equation 70 into A plus 21 into B plus 15 into C. Therefore, 70 into 2 already we have taken, therefore, substitute it. So, that 70 into 2 plus 21 into 4 and 15 into C is 3. So, that the resultant of this 140 and 84 plus 45 equal to 269. Therefore, you take the value of 269 with respect to 105, the remainder is 59. So, it follows that the selected number is 59. So, this is interesting one, and we can easily calculate if a system of linear congruence or simultaneous system of linear congruence comes, how to calculate the values of x. So, next we will go to one example, call it as a broken eggs problem. So, very interesting. So, first listen the theory and then understand the theory, how it is converting into problem. An old woman goes to market and a horse steps on her basket and crushes the eggs. The rider offered to pay for the damages and asked her how many eggs she had brought. She does not remember the exact number, but when she had taken them out two at a time. There was one egg left. The same happened when she picked them out 3, 4, 5 and 6 at a time. But when she took them 7 at a time, they came out of even. So, what is the smallest number of eggs she would have had? So, this question, and remember this question and then convert it into a mathematical equation is supposed to be called as modeling of this problem, and let us see. So, the number of broken eggs x must satisfy x identically equal to 1 under modulo 2, or x is identically equal to modulo 3, or x is identically equal to 1 under modulo 4, x is identically 1 under modulo 5, x is identically 1 under modulo 6, or sometimes it may not come under modulo 7. So, he took one and then left 2, 3, 4, 5, 6. So, this is the way we can write mathematically the system of simultaneous linear congruences. See, the first congruence says that x is odd. So, we shall keep this in mind and ignore this congruence. The use of our theorem, we will also omit the congruences x is 1 identically equal to 1 under modulo 6. So, that the moduli of the remaining congruence 3, 4, 5 and 7 are relatively prime in pairs. So, this way we have to understand. Now, according to the Chinese remainder theorem indicates that there is a unique solution of modulo 420. The 420 can be written as the product of this number 3 into 4 into 5 into 7, which is calculated by M3, M4, M5, right, M7. So, for M3 what you have to do is 420 by 3 you have to divide. So, 140 will come, and M4 you have to take 420 by 4 equal to 105 will come, and M5 equal to 420 by 5 equal to 84 will come, and M7 we have 420 by 7 equal to 60 will come. So, this is the first step you have to evaluate with the help of the formula from Chinese remainder. Once you evaluate it, ultimately you have to find the inverse, that is most important, then only we can apply in general form of the Chinese theorem. So, every time we require the inverse of corresponding M3 is 140, therefore, the inverse of 140 you have to find out under modulo 3. So, we have the value of this one xy is identically equal to 1 under modulo 3, and then we have 140 into y identically equal to 1 under modulo 3, we have the value is 2. Similarly, you have to calculate 105 whole inverse under modulo 4 equal to 1, and then 84 inverse of under modulo 5 is of 4, and then 60 inverse of modulo 7 is 2. So, we have what the rule capital M by M1 into M3, right, that is M3 of this value into inverse of M3 inverse plus and so on, the final steps you have to do that. Now, you substitute it. So, the value of this one is 1 into 140 into 2, and then 1 into 105 into 1, 1 into 84 into 4, and 0 into 60 into 2. So, we have 280, 105 and 336. So, if you add them, we have the result 721 under modulo 420. So, the value is 301. So, this way we can calculate the values of this problem. So, from this solution we can infer that x is odd and satisfy x is identically equal to 1 under modulo 6. It is the smallest solution of the broken eggs problem. So, this is very interesting and very useful for understanding the real time problem. Once again I do that, come across the Chinese remainder theorem and followed with the Chinese remainder theorem. We are going to discuss some more interesting theorem is Wilson theorem and Fermat-Little theorem, and this Wilson theorem and Fermat-Little theorem are more useful to testing of a primality. Then let us start with the first Wilson theorem. If P is a prime, then P minus 1 factorial is identically equal to minus 1 under modulo P, right. P is a prime, note that point, and P minus 1 factorial find out. Definitely the value is identically equal to minus 1 under modulo P. So, let us start with one example. Let P equal to 7. P 7 is a prime number, and we have 7 minus 1 factorial is nothing but 6 factorial, and 6 factorial can be written as product of the number 1 into 2 into 3 into 4 into 5 into 6. So, that we will rearrange the factor, the product grouping together like a pairwise inverse of the modulo 7. We note that, and 2 and 4 are inverse of the other, because if you product 2 into 4, it becomes 8 under modulo 7 is 1. Similarly, you pair 3 and 5, 3 into 5 is 15 under modulo 7, then it is identically equal to 1. And also you have to take the other pairs. So, I think maximum pair we covered. So, 2 into 4, 3 into 5 are the only the 2 pairs corresponding to modulo. Therefore, we have one more ideas, that is 6 and 1 left. Finally, we do that. Now, we have 6 factorial can be written as 1 into 2 into 4 and 3 into 5 and to 6. Therefore, it is identically equal to 1 into 6. So, 1 into 6 you take it under modulo 7, definitely that value 6 under modulo 7 is minus 1. So, we have verified the special case of Wilson theorem. So, that is the meaning of, if you take P equal to 7, 7 minus 1 factorial is 6 factorial is identically equal to minus 1. So, this is the meaning of Wilson theorem. Now, we have a proof. Let us start with P equal to 2, because P equal to 1 is a trivial case. We ruled out P is prime, note that point. P equal to 1 is neither prime nor composite. When P equal to 2, we have P minus 1 factorial, which is identically equal to 1, or which is identically equal to minus 1 under modulo 2. Hence, the theorem is true for P equal to 2. Now, let P be a prime greater than 2. Now, using the theorem that is 3.7, in the sense that we have a theorem in one is inverse of the other. So, we do not want that number. So, using the theorem for integer a with 1 less than or equal to a less than or equal to p minus 1, there is an inverse a inverse such that 1 less than or equal to a inverse less than p minus 1, where the product of these a inverse is identically equal to 1 under modulo 1, and we have a proportion that the only positive integer less than p, that their O inverse are 1 and p minus 1. Therefore, we can group the integers from 2 to p minus 2, and so that p minus 3 by 2 pairs can get it of the integers. Therefore, the product of each pair is congruent to 1 modulo p. Hence, we have 2 into 3 into 4 into and so on p minus 3 into p minus 2, which is identically equal to 1 under modulo p. Now, we conclude that the proof by multiplying both sides of the above congruence by 1 and p minus 1 to obtain. So, p minus 1 factorial is nothing but 1 into 2 into 3 into and so on p minus 1 terms. So, we have the the pair 1 and p minus 1 only remaining terms, rest of them will be 1 because one is the inverse of the other. Therefore, p minus 1 you take it under modulo p is identically equal to minus 1, hence we have a proof of Wilson theorem. Now followed with that the theorem is if n is a positive integer such that n minus 1 factorial identically equal to minus 1 under modulo n, then n is a prime. So, the proof is assume that n is a composite integer and then n minus 1 factorial is identically equal to minus 1 under modulo n using the Wilson theorem. Since n is a composite, n can be written as a product of two numbers, prime numbers, one less than a less than n and one less than b less than n. Since a is less than n, we know that a divides n minus 1 factorial because a is one of the n minus 1 numbers and multiplied together to form n minus 1 factorial. Since by Wilson theorem n minus 1 factorial is identically equal to minus 1 under modulo n, it follows that n divides n minus 1 factorial plus 1. So, this means by use of the proportion that a is also divides n minus 1 factorial plus 1. From the proportion a is also divides n minus 1 factorial and a divides n minus 1 factorial plus 1. Therefore, we can conclude that a divides n minus 1 factorial plus 1 minus of n minus 1 factorial. Therefore, we have the value is 1. So, this is an obvious to contradiction that a is greater than 1. So, this way we can prove that the following theorem of Wilson. Now, we have a example 6 minus 1 factorial is nothing but 5 factorial which is equal to 120. 120 under modulo 6 is there is no remainder is 0. Therefore, this theorem verifies that fact that 6 is not a prime. Next, we are going to discuss the Fermat-Little's theorem. If p is a prime and a is a positive integer, that is the greatest common factor GCD of divisor is a and p is 1 and p does not divide a, and then a power p minus 1 is identically equal to 1 under modulo p. Then the proof rather we can write this problem as a power p into a power minus 1 is identically equal to 1 under modulo. So, a power p is identically equal to 1 by a inverse. This implies a power p is identically equal to a under modulo p. So, this way we can write the Fermat's Little theorem. So, consider the p minus 1 integers. So, a, 2a and so on p minus 1 into a. So, none of these integers are divisible by p. So, if p divides j by lemma, p divides j, since p does not divides a, this is impossible because 1 less than or equal to j less than or equal to p minus 1, and further no two of these integers a, 2a and so on p minus 1 to a are congruent modulo p. To see that, assume j a is identically equal to k a under modulo p. Therefore, according to corollary C, the GCD of the number is 1. We have j is identically equal to k under modulo p. So, this is not possible. Therefore, j and k are positive integer which is less than p minus 1. So, we have what the integers a, 2a and so on p minus 1 into a are set of p minus 1 integers, all are incongruent to 0. Therefore, no two congruent modulo p. We know that the least positive residue of a, 2a and so on p minus a taken in some order must be the integers 1, 2, 3 and so on p minus 1. As a consequence, the product of the integers a, 2a and so on p minus a is congruent under modulo p to the product of the first p minus 1 positive integer. Hence, a 2a and so on p minus a equal to 1 into 2 into 3 into and so on p minus 1 under modulo a p. Therefore, a we taken up to a power p minus 1 terms, right, and then p minus 1 1 into 2 into 3 and so on p minus 1, we have p minus 1 factorial, here p minus 1 factorial under modulo p. Therefore, we have p minus 1 factorial get cancelled, and then we have a power p minus 1 identically equal to 1 under modulo p is a proof of these ideas. For example, you take p equal to 7 and a equal to 3, then we have 1 into 3 is identically equal to 3 under modulo 7, and 2 into 3 is 6 under modulo 7, and 3 into 3 is 9 under modulo 7 is 2, and 4 into 3 is 12 under modulo 7 is 5, 5 into 3 is 15 under modulo 7 is 1, and 6 into 3 is 18 under modulo 7 is 4. Consequently, the pair 1 3, 2 3, 3 3, 4 3, 5 3, 6 3 you take it. So, that corresponding value under modulo 7 put it 3, 6, 2, 5, 1, 4. So, that 3 power 6 equal to 1, 2, 3, 4, 5, 6 and corresponding 3, 6, 2, 5, 1, 4 under modulo 7. Hence, 3 power 6 into 6 factorial equal to what? This is divisible, and we have a 6 factorial under modulo 7. Therefore, 3 power 6 is identically equal to what? Modulo 7. So, this way we can calculate Fermat-Little theorem using the example. Now, we have a theorem. If p is a prime and a is a positive integer, then a power p is identically equal to a under modulo p, and we have a proof, that is p does not divide a. According to Fermat's Little theorem, we know that a power p minus 1 is identically equal to 1 under modulo p. Multiplying both sides of this congruence by a, we find that a power p is identically equal to a under modulo p. So, if p divides a, then p divides a power p as well. So, that a power p is identically equal to a under modulo p is 0. So, this finishes the proof, since a power p is identically equal to a under modulo p if p does not divide a and if p divides a. So, this way we can prove that Fermat-Little theorem. For example, we find the least positive residue of 3 power 201 under modulo 11 with the help of Fermat's Little theorem. So, we know that 3 power 10 is identically equal to 1 under modulo 11. Hence, 3 power 201 can be written as 3 power 10 into 20, 3 power 10 whole power 20 into 3, right. So, 201 can be written as 200 plus 1, right. Therefore, this can be written as 201 is 200 plus 1, and then power we can split it, and 3 power 10 into whole power 20 into 3, and this exactly is therefore only 3, therefore under modulo 11 we have the value is 3. Now, we have a theorem. If p is a prime and a is an integer with p does not divide a, then a power p minus 2 is an inverse of a under modulo p. So, the proof is if p does not divide a, then Fermat's Little theorem tells us that a into a power p minus 2 is equal to a power p minus 1 identically equal to 1 under modulo p. Hence, a power p minus 2 is an inverse of a modulo p. So, from the example of the theorem previous, we know that 2 power 9 can be written as 512. 512 divided by 11, the remainder is 6, is an inverse of 2 under modulo 11. So, based on the corollary, if a and b are positive integers, and P is a prime with P does not divide A, then the solution of the linear congruence Ax is identically equal to B under modulo P or the integers such that, so x can be expressed as A power P minus 2 into B under modulo P as per the Fermat's little theorem. So, we can directly give the solution to the problem. So, the proof is, assume Ax is identically equal to B under modulo P. Since P does not divide A, we know from the theorem of Fermat little theorem and Wilson theorem, we have A per P minus 2 is an inverse of A under modulo P, multiplying both sides of this original congruence of A per P minus 2, we have A per P minus 2 into Ax is identically equal to A per P minus 2 into B under modulo P. Therefore, so we have the cancellation of this one and bring it to one side, x equal to A power P minus 2 into B under modulo P. So, because this becomes A power P minus 1 x, and this becomes 1, and then we into x equal to this. So, this way we can write the proof of the theorem. So, there ends possibilities of the proof of the theorem.